You can see where I screwed up here. Diffraction in crystals is a well-documented effect that, in a crystal structure, you have layers of atoms, that are some distance apart. And if you, shoot light at this layer, one beam might reflect while another coming in, passes through the first layer and then reflects off the second layer, okay, and comes back. And these two waves have a path length difference, and so they can interfere with one another. If we extend this back, if we call this angle theta, and draw in our normal, you can see that the path length difference up to here is the same. Okay, it's from this point on that there's a difference in path length, and the same here. Path length difference from here on is the same as the path length difference from here on. And so the path length difference is this plus this. And if we say these two layers are a distance d apart, this angle is theta, which means that this angle is also theta. If that angle is theta, and we make, these are not extended out. These are making a right angle to this reflected and incident beam. And if they're making a right angle, that means that this would be 90 minus theta, and then this would again be theta. So if that's our theta, this is a right angle. Then this d is this hypotenuse as well, and this right here is a d sine theta. So then our path length difference is twice that. Path length difference between these two is d sine theta. So our delta L, our path length difference, which means that we have constructive interference wherever 2d sine theta is equal to some multiple of the wavelength. And m starts at 1. M can't be 0 because this distance is not 0. Right. And so then, when crystals create this sort of diffraction pattern. Okay. Now, in 1928, these guys, I mentioned the two-slit experiment, but these guys, Davison and Germer, performed crystal diffraction with electrons. And up till this point, it had only been used for light. And not only did they get an interference pattern, so that they got an interference pattern which confirmed some kind of, which confirmed that, there is a wave behavior for electrons. And not only so, but the interference pattern was such that the wavelength, the interference pattern fit in with the de Broglie prediction for what the wavelength would be. So this experiment was kind of a big deal in terms of confirming de Broglie's hypothesis about the wavelength of a particle. And since then, this experiment has been repeated with neutrons and hydrogen and helium atoms, sort of smaller particles that would have a noticeable wavelength. Yeah. And just another point of note is that electron microscopes are useful in medical imaging because this wavelength on the order of 10 to the minus 10th is much smaller, because the wavelength of an electron is smaller than the wavelength of any sort of visible light, and any electromagnetic radiation that has a wavelength that's as small as an electron is dangerous to living cells. Gamma rays kill things. So because this wavelength is smaller, you can get resolution that's higher, and so you get better images of really small stuff with an electron microscope than you can with a light microscope. Now, I'd like to return to the question of wave-particle duality, because philosophically speaking, this has some serious issues. Okay, let's think about it in terms of that two-slit experiment. Okay, light is a wave. If we think of light as a wave, it interferes. Whatever. There's no big deal with that. We get this pattern of bright and dark fringes, and there's points of constructive and destructive interference, so that some are brighter than others. There isn't really an issue with that. Now, particles, we get these bright and dark fringes. But if we think of them as photons, they're still bright and dark fringes. And if we shoot a beam of photons at them, now these photons just happen to be hitting the more photons hit in the bright regions, and fewer, if any, photons hit in the darker regions. That seems okay on the surface too. But then the question arises, in the photon, what is interfering? If we think of light as a wave, it poses no problem that, waves interfere. We know how waves on a string operate, and there's constructive and destructive interference. But if we just have photons hitting our screen, then what on earth is interfering? Okay, you could say, there's a beam shot and maybe one photon interferes with another. Okay. But then here's where it becomes a problem. We do our two-slit experiment. We shoot one photon at a time. Now, you'd think, shooting one photon at a time, there shouldn't be anything to interfere, right? It's a photon, right? If you think of it as a particle, it's going to go through one slit or the other, and it'll hit the screen somewhere. So there shouldn't be anything to interfere. And if you shoot one photon at a time, you start recording their locations, and they do seem to, hit random locations, seemingly random locations. I'm going to put quotes around random because we haven't established that these are random yet, but they seem to hit at random locations. And then over time, this interference pattern still emerges. So that begs the question, how does this photon, what is this photon interfering with? A photon if it was just a traditional particle, it's shot through this slit, there wouldn't seem to be any reason that it should skip over hitting these certain regions. We've got our interference pattern, right? And if you're shooting one photon at a time, how does the photon know that it's not supposed to hit, at this minimum? How does it know that it's supposed to hit near the maximum? But it does. If you shoot the photons one at a time, and you record them, you get a bunch of photons hitting at these maximums, and no or very few photons hitting at these minima. So if we're shooting one photon at a time, what on earth is interfering? That's just a kind of a mind-blowing thing. Now, okay, so that's a weird thing. Now we do it with electrons. And I've told you that you shoot a beam of electrons, interference pattern shows up. You shoot electrons, one at a time. This same thing happens. This interference pattern occurs. What's interfering? Okay. Now, here's where things get, this is just so far this is confusing. We don't know what's going on. But now here's where things get weird. If you put a little detector, at each slit, and this detector, it's going to ping, it's going to give you some sort of indication whether the electron or photon in question passed through this slit. So if it passes through the top slit, this detector goes off, that it passed through that slit. If it goes through this slit, this detector goes off, passed through the bottom slit. When you put these detectors here, suddenly now, you shoot a bunch of electrons, a bunch of photons, you know which slit each of went through. What happens? there is no interference pattern. There is no interference pattern that emerges when you put these detectors here. If you put the detectors here, what you get is a whole bunch of stuff hitting kind of straight in front of each slit, and then very little as you go off, which is kind of what you'd expect to happen if you just like say you had two holes and you just kept chucking baseballs at them, for example. You know, they'd all hit pretty close to the opening. You wouldn't expect them to bend. They're baseballs. They don't just bend in the air. And that's what happens if you put these detectors here. So something about putting these detectors here has changed how the system is behaving. And the conclusion that seems unavoidable is that knowing which slit the photon or electron passes through somehow changes the behavior of this photon or electron. And the only reason that it would make sense for so the idea that they came up with was that when you shoot them one at a time, this photon or electron, if it creates this interference pattern, even when you shoot them one at a time, it must be interfering with itself somehow. But these detectors, that they break down the interference pattern breaks down if you know which slit the photon or electron passes through. So that has led scientists to the conclusion that when you're not measuring this, there is some sense in which the photon or electron passes through both slits simultaneously. There is a sense where it passes through both slits simultaneously, but then when you measure it, then it has a 50% chance of passing through one slit or the other, okay? And you don't know, and it's sort of a probability wave that's interfering and causing the particle to hit the screen in one place or another. But if you know which one it passes through, then that probability wave breaks down because now you have probabilities of 1 and 0, and so there's nothing left to interfere with. So in a sense, you have a 50% probability, and if you don't know which slit a wave or particle or a photon or electron passes through, it in a sense passes through both slits. And if it passed through one slit or the other and you just didn't know which slit it passed through, there wouldn't be that interference pattern, because if it just passes through one slit, it's going to hit near the opening of that slit, and that'll be that. But it doesn't do that unless you put the detector there. And so in some sense, by measuring it, by learning something about the system, you change the system. And that is one of the most bizarre things about quantum mechanics, is that by taking a measurement, you change the system. And so and then there's this idea also of indeterminacy. It passes through both slits, so there is this sense of indeterminism. The particle hasn't passed through one slit or the other. It has, in some sense, passed through both, or you can't tell which one it passed through, because if you tell which one it passed through, it doesn't interfere anymore, and it changes things. So there's this sense of, there's this indeterminism, and that everything is just this sort of probabilistic sort of system, which is weird, and it caused a lot of worldview problems for scientists, and still kind of does. And we're going to take some time in class to talk more about that and maybe one or two other things related to philosophical issues that have been raised by quantum mechanics. If this doesn't make any sense, that's okay. It doesn't make sense to anybody, and we'll talk more about it in class.